Yeah, I'm ready.
Okay. We're happy to have the code from our own department talk about stable individuals from 2D symmetry.
Yeah, thanks for giving an opportunity. So, what I'm going to talk today started as a project with Mina, Peng, and Yixuan. And later, when I tried to understand what actually we're trying to match, I collaborated with Andrey Smirnov on an easier version of the objects we consider. So in the original project with Mina, we had equivalence of two triangulated categories. We had the derived Fukaya category for a space with superpotential of it, and we had derived category of coherent sheaves, equivariant coherent sheaves. We usually, so this guy has only some information about symplectic structure here, and we call it A side. And this is B side. And there's an equivalence between these two things. As predicted by 2D mirror symmetry. In the talk today, I will try to focus on one particular case of it. It will be type A1. Let me start with what the B side is. At least for me personally, this side is more understandable than the other side. You could have different preferences. But yeah. Okay, so what do we have on B side? On B side, we have X, that is the Coulomb branch of a quiver, a framed quiver that is of type A1. So here I have K, here I have N. Okay, and here we have, I will think that N is larger than 2K. Peng at the very beginning of the semester had discussed this construction when you have N is 0. So that's like very different story from what I'm going to do now. Okay, and now if you prefer quiver varieties or equivalently Higgs branches of quivers, you can write it as a quiver variety for another framed quiver. That looks like this. And so we see K here, and here we'll have N-1 nodes. So my condition exactly ensures that I can write it in this way if you want. Sorry? Sorry, I don't know what. N greater than K? No, because like I have twice here. You mean if I'm in the other chamber? Yes, I'll just say that this is, but then I don't want to go in this case, okay? Not quite, but okay. Like once again, I don't want to put 0 here. You mean just good? Okay. Okay, never. Okay. So when I discussed before this talk with somebody in the audience, they sometimes prefer slices in the fine Grassmannian. So just as another description, that's resolution of a slice in type A1 of form A. If omega check is the fundamental co-weight, then it's in slice of a fine Grassmannian in type so that will be our main thing on one side. Okay, and what is good about this X? X is holomorphic symplectic. Even though on B side we'll use only it as algebraic variety, having holomorphic symplectic structure gives us interesting properties of it, escalating promises. And I also said that I want to take equivariant coherent sheaves. So on this guy, there is a torus section, and it's a product of two tori. This is just the maximal torus in A1 type reductive group. So actually, it's also C star, and it acts on X by symplectomorphisms. It respects the symplectic structure. And the other thing, it scales the symplectic structure. So I will call weights that come from this part H bar, and weights that come from this is alpha. So that more or less explains what we have on this side. And if you want to have something less abstract in your mind, let's discuss special case. If K is 1, then X is the resolution of an singularity, which is just I take the plane and quotient it by Z over Z. Right? And if I set both n and k to 1, then X is just, which should be the most familiar example here. Yeah, and sorry, understood. Yeah, I want n minus 1 to be. Yeah. So in this case, we have like in this picture, in the sense of this picture, it's just self-dual case. It depends what construction you consider. So I think it's the easiest in the quiver picture, you just take two framings and you just scale them differently. So you scale one with A and the other with A inverse, and that's it. Here, it's naturally, it comes from construction where you have action of G of the reductive group that is in here of type A1. And actually, the thing that survives is only the maximal torus, and it acts there. Most likely, yes, but the scaling should be due to like how many line bundles I have on Higgs branch, and like there is only one node. So yes. T star P1. So P1 is just like the Riemann sphere, and then I take complex cotangent bundle, and it's complex of dimension 2. Yeah. So it's automatically symplectic. There is torus action on P1, and more or less you can check that all these guys work there. Okay. Yes.
Wait, so the specific torus action on T star P1, how does it act?
So A just scales P1, and H bar just scales the fiber.
So how is A a symplectomorphism then if it scales on P1?
It scales P1, and accordingly it scales this thing. If we have any transformation of the base, it defines me as symplectomorphism, right? If you take a Hamiltonian that is dependent only on coordinates here, then it defines you as symplectomorphism.
It feels like it should increase the volume to scale it up P1, but
no, but it so it scales P1, but if I take the fibers over 0 and infinity, it also scales the fibers. Yeah. So like if you look at this situation, you will have coordinates are scaled, but the fiber is shrink, exactly to preserve the symplectic form. Exactly. Mm-hmm. If we study anything equivariantly, we are quite often interested in torus fixed points. So here, the torus fixed points is fine. There are finitely many of them, and their number is just the choose number. And we will consider attractors to the fixed locus with respect to the symplectomorphic torus. Maybe one more thing to say that actually the fixed points with respect to x, with respect to the smaller torus, with respect to bigger torus. Okay. Keep it less abstract. In K is equal to 1 case, when we resolve the AN singularity, we have the exceptional divisor. And we have two special fibers at the end of this chain, which come from invariant axis in A2. And what are my fixed points? My fixed points are exactly the nodes here. And what is an attractor to a point? It depends on the choice of how do I act with respect to positive co-characters or with respect to negative co-characters. So if, for example, I take this point, one attractor could be everything that is attracted from this direction. And another thing could be attracting from this direction. And attractors are half-dimensional. Attractors are Lagrangian. Because my torus is symplectomorphisms, X by symplectomorphisms, if one direction is scaled with by shrinking, then the dual direction should be should become bigger, right? That's exactly your point about preserving the volume. So I see if I scale it with respect to one character, these points will approach this thing, but if I scale with respect to inverse of that character, this will be in the attractor. Okay. So now the main object will be the core. So we say that the core, which I will call by straight x of x, is the union all attractors to the fixed locus. I take all chambers, all points. So all points in this, all generic co-characters in A. So all chambers, if you want. Okay. So in this picture, that will be exactly the wine lines I drew. Okay, that will be exactly the exceptional divisor plus two fibers, because for every part of it, it's easy to show that it will be attractor to something. Okay. Is this clear? Yes? Like this chains of P1s, right? So there is a chain of P1s and two A1s. I'm just saying that union of this one-dimensional thing is actually what I call the core here. Okay. And as you can see from this picture, X is singular. It could everywhere where the fixed points are, it has local behavior like a cross, and in higher dimensions it would be similar. Okay, but also it's holomorphic Lagrangian. Because the attractors were, and also it's T invariant. Well, it's obvious that it's A invariant. It was defined as union of A invariant things, but also if you think what happens to the symplectic form, it's easy to show that it's T invariant. And there are special objects in equivariant K theory of X. It's straight X. Here I write straight X first.
There's also a definition for X being the fiber.
Sorry, could you hear me?
So this straight X is also the fiber of some complex model map of this A.
No, it would be symplectic if it was a symplectic reduction, right?
The fiber of.
Ah, the fiber. No, no, it's not. You can do something close to it. You can map it to affinization and then a invariance of it. So you could construct it as fiber of something, but it will be more complicated. Let's just not go there. And it will be not useful for my talk. So what are special objects in this thing? So first of all, it's the structure sheaves of fixed points. Because all fixed points of this guy are here, that's actually the same. Right? And localization theorem says that after you localize this, this is a basis. So we have effective way to do something about this guy. And second thing we want to consider is stable envelopes. That are more or less refined notion of the structure sheaf of the attractor. And here I need to specify the chamber if I'm scaling with positive co-characters of negative. So there are two versions of it, positive and negative. And that will be two versions. I'm suppressing some data that on which are involved in the definition there, but some part is just more or less thermalization. And there is an important piece of data that I'm hiding, but if somebody can catch me later and ask, oh, where it is in your future picture, I'll be happy. But okay, so in my example, if I'm taking this thing, and I'm taking the simplest choice as possible, consider this point, then the stable envelope with respect to one chamber would be the attractor to this point and everything that is attracted to this thing and everything that is attracted to this. And here it turns out that it's more or less what you need to have. So let me call it step plus at this point. And you have, if you scale with in the opposite direction, that would be step minus of P. These are the classes. And it's not hard to show that if the fixed points were basis after localization, these guys will be also basis on after localization. Just the transition matrix from one to another is upper triangular with non-zeros on the diagonal. Okay, so these are my favorite objects. And usually when people study this picture, they usually discussed as classes in, as Peter was trying to force out of me, in the key theory of the whole thing. But that's just take the push forward.
So the theories, like you put some pictures, which makes sense, but
These are support of certain classes there. So if you want, this is cohomological limit where it's actually like just fundamental cycles of this, but you could upgrade it to K-theoretic picture and say that it's some sort of structure shift that is supported here, or like structure shift twisted by a line bundle, something like this.
other twists or not?
Sorry?
Other twists or not?
It depends. I will not discuss this part, just like in cohomological limit, they will degenerate into only one picture that will look like this. Okay, so they're discussed as classes in here. So i.e. their images under the push forward. I consider it. And because this sits naturally in this, we have this map. So I just push forward along the inclusion. So for fixed points, that's easy. They're already defined as push forward of the along the inclusion of the point. So just you forward push it. And for stable envelopes, more or less, that's one of the axioms in their definition that they come from these guys. They're push forwarded from this space. Yes?
So this is a question of a much earlier point, but for all these pictures you're drawing, shouldn't the resolution singularities have like a chain of ones where it connects in a circle?
I'm drawing a chain of P1s.
Oh, like how it doesn't connect back up to it?
It doesn't connect back up. Yeah, it should be the intersection between them should be exactly the pairing in AN root system, or yeah, AN. Right. So just the further ones are not connected.
Okay.
Right, just like the linear curve. Yeah.
The stabilizer is not just the attractor; it's like a chain of attractors. Each attractor going to the next attractor.
The stable envelope, yes, it's yeah. If you try to modify this picture in any way, for example, a smooth a node here, you will see that it's better to define it like in a continuous way. There are other reasons why you should do this, but that's like one of them. If you want to consider it in a family and deform them as symplectic variety, these guys are the ones that survive. These are the ones that could be deformed, that come in a family. Yeah. And surprisingly, that's not why they're called stable. They're called stable because they are like attractors, like stable thing in that sense. But okay, they're also stable in another way. Deform in family, they deform well. Okay, so two favorite objects I like in this thing actually come from this space.
I guess I'm just usually when people talk about divisors of type A and they have like a whole circle.
That's strange.
If you want to generate this, physically the space is really singular. You get that kind of that kind of description, because really what you're trying to say a little bit better. true that if you look at the category of all sheaves on the sky, that is generated not just by the objects supported on the P1s, there's also the affine node, which is like the sum of all of them put by line. And mirror symmetry makes this affine thing completely geometric. It's not mysterious at all. But on the coherent sheaf side, it's a little bit mysterious. You would discover, for example, if you thought of the alien surface as a quotient, as he did originally. In that quotient description, you naturally come up with a Hilbert description, which is called
Okay, so let's see what we have on B side. We had the derived category we are interested in, and another derived category that we could be interested in. And there are two functors between them. So we can push forward along the inclusion and pull back along the inclusion. Right? And we want by the end of the day to study some relation here. Let me write it currently. And Mina's suggestion was that you can actually use 2D mirror symmetry here as well. So there is some sort of corresponding objects here. Let me call it straight Y, straight W. And you have a corresponding pair of functors here as well. Also adjoint. So you can take this picture and completely mirror it here. And since I want to study some objects here that actually come from here, I will try to translate them into objects here and figure out something about them. I will try to construct precise identification here. And as a side effect, it will, if I can compute something on this side, it will tell me something about this. General key. Just I keep k equals to 1 because it's the most familiar, I think, for. Okay, and for this thing, it's slightly easier to describe what the space is that when it is to here. That's why I kept not saying what I actually have here until I'm on this step. So on A side, we can describe what Y is. Y has an easier description than the curly Y. So if we fix endpoints in C star, about which I'll think that it's a cylinder, I introduce Z1 and here, some fixed points that are distinct. Then Y is the space of unordered pairwise distinct collections. Unordered collections of k pairwise distinct points on without n. So in addition to these points, I'll have y1. These ones are assumed to be fixed, and this one vary. And if you want to know what the curly y is, curly y is open part of it. Open dense part of curly y is a complex story fibration over y, which in particular will give me the two functors. Okay. In this language, W is multivalued. On this side, it's multivalued. And this multivaluedness is exactly mirrors the equivariant action on the torus action on the other side. If you try to do it multi-covariantly, usually in 2D mirror symmetry, you take single valued superpotential. But in our setting, we will take it multivalued exactly for the reason that that we want to consider equivariantly here. So we are interested in e to the minus w. And multivaluedness leads to monodromy. So this thing, it has monodromies. The dimension of curly x is no. 2k is on the other side. Y is 2k dimension. That's it. Yeah, right. Right. Sorry? Well, like y and actually like
Curly y, curly x was complex. Straight line.
Yeah. They're closely related by hypercurl rotation. So, yeah. So this thing has some monodromies, and it just comes as a product that you can associate to the quiver. And let me just write what it is. So first of all, you have terms like this, where lambda is not an integer. That's why you have multivaluedness. Product over 1 minus yi over k. And let me write it here. Sorry? Sorry, lambda 0 is? Not an integer. That's exactly the multivaluedness, yes. So, yeah, and finally times the product of i's to lambda 1. So lambda naught and lambda 1 are exactly something that control the monodromy. And we will usually deal with their exponents. So h bar would be e to the 2 pi I lambda naught. So it's better not to be 1. And alpha also is e to the pi I. And I'm introducing this notation, as you see, to exactly match something on the other side. Okay, so it matches with my ground ring on the other side, K0 the point, that is
The h bar and the alpha are weights with respect to individual fixed points on your B side, correct?
sorry, could you repeat?
Is it true that the h bar and the alpha are weights with respect of your torus action
Of T, yes.
fixed points? Like each fixed point has its own.
No, it's weights, just it's C star times C star, and I'm just looking at the weight lattice of it.
Oh, okay.
And I just call the one that corresponds to one direction H bar, the other alpha.
Okay, so these are like a basis vector.
Yeah, and like this is exactly the coordinate ring on the torus.
Okay.
From the other side, I see it.
So this is like basically the torus action on the B side corresponds to the superpotential on the B side.
Yes, multivalidness of it, like monodromies. Okay, are we good about this? So that's the setup that we work with Mina in. And now, unfortunately, I'll take this beautiful picture and just throw away a lot of information. Just kill everything. We'll decategorify it. Okay, so first of all, I already tried to say that I'm interested not actually in the derived category of coherent sheaves, even though it's great, but I'm interested in K theory. So I just take coherent sheaves, anything, and I just do equivariant K theory of it. Apply K naught to it. Cool. And now what happens to the Fukaya category under taken K naught? Well, what are objects here? Objects are Lagrangians. Right? This is something described in terms of the symplectic structure of my space. And also, each Lagrangian is equipped with a choice of e to the minus w branch or lift of it. Sorry? Yeah, so it's not one choice. If I have one, I'll just add, I could just always multiply by h bar or alpha, and that will be it. But you have exactly the same freedom here. If you take an object and you say like, okay, I considered it some of its linearization, let's say of a line bundle, but now I will be able to multiply it by characters and it will still be a good object. So exactly the same degree of freedom. That's amazing. So my son is at the age where he likes to play, look at the pictures and find 10 differences. So here I'm playing the opposite game, like look at the picture and find 10 similarities. Okay, so if I just look at this, and we know that they are defined up to certain Hamiltonian Hamiltonian deformations and so on. When you see this picture, something defined up to deformations, you guess what it could be. It's just you take the homology of the corresponding Lagrangian, right, in my space Y. But also I have to somehow remember the choice of the superpotential there. So I will just introduce rank 1 local system. Local system with monodromies of e to the minus w. And I like this object more because it's something you can explain to an advanced undergrad, like what are homologies and how to take them with coefficients in local systems. Okay. I'll go there. Okay. So first of all, because it's like you mean here. Yeah. Here. So why I don't call it K theory of it. Okay. There is a statement. It's that K theory of this thing. Sorry. That this category is split generated by critical points by Picard-Lefschetz theory. But if I go to Zeidel's book on it, in the introduction, it says that it just split generates, not generates. So we're not sure if these classes, the thimbles actually generate the K group. I could not find a reference with
we actually know how to generate.
How to split generate. And split generate is not enough to generate the K. Okay. In the real sense.
We know it's that generated. In a sense, more real than anything. In the sense as real as the most elementary example, the only example of satisfiable in that sense. You know?
Okay, let me put it this way. I try to understand how Zeidel's proof works, and I'm less comfortable with this side, and just direct statements I could extract from there without writing a sequel to his book. I couldn't make the statement precise, but we expect it to be K theory of this thing. Okay, I just don't want to straight lie that I know that this is. I personally don't know if this is a K theory of this thing, but K theory definitely suggests ontoship. Is okay? And in so W is holomorphic symplectic. So we know that critical points of W in algebraic topology, it gives you Picard-Lefschetz theory, which is a statement about generation of more or less this guy. And just people who worked on Fukaya categories said that you can generalize it to Fukaya categories.
So it's true, the strict theorems of Zeidel's book don't apply. But because we know how to actually generate it, we know all possible subtleties of the sort. So, and it's not true the critical points generate. You need a little, you need critical points in infinity and then it's okay.
I don't understand how to prove it. I personally, I don't want to lie. Yeah. So no, just like, yeah. I will personally compare these two decategorified guys, and they have relations to K theory of these things, so they'd better be the same if we want. these guys to have categorical equivalence.
Yeah, I mean, at the decategorified level, it's something.
Yeah, so like I can prove decategorified statement modular, like if this step is exactly what we need. Okay, so I somehow didn't finish writing this guy. So first of all, because they are Lagrangians, it should be just middle dimension. Right. And second of all, this guy is not compact. And I want to allow cycles that go to infinity. So I'll take parallel here. Okay. So in the rest of my talk, I'll just identify these two guys. Sorry? Borel-Moore means that they are not compactly supported, that they can escape to infinity. Yeah, yeah. If you remember our favorite cycles, they definitely escape to infinity. So yeah. H bar. Just like in the universal family, it acts on the base. Ah, you mean here? It's not action, it's monodromy. If you go to curly Y, it's actually a monodromy around some C star, around the fiber. So in the fiber, it's actually monodromy around like the fiber. So how you can imagine like this H bar in terms of C star. Yeah, but it's like description of like monodromy of this function. But if you want to actually see it like in just C star, where it is C star, it's upstairs. Upstairs, the monodromies become easier. They will be just. Oh, I erased it. We have the picture that we have the whole X, curly X, is mirrored to curly Y, and curly Y is. Should I write it somewhere here? So we have X on this side is mirrored to curly Y, and here I have a certain subvariety of it, and it's mapped to this guy. So we have mirror symmetry here, and some natural pairs of adjoint functors between these things, independent on two sides. So, but because I'm interested in classes that come from here, fixed points and stable envelopes, I will just more or less study this guy.
Yeah. No, it is two.
Yep.
So before you go to the A side, you had something like from the core of the B side, straight X go to curly X. Is the K theory, is that surjective? Is that right?
It's isomorphism after localization because they have the same fixed points. Okay. So Peng asked what's the relation between K theory of straight X and K theory of curly X. And they claim that they are the same because after localization, they're the same because they have the same torus fixed points. this is singular. So in particular, you have to ask what version you take. Do you take the perfect version, or you take like actually that works with coherent sheaves and so on. So like there are more flavors here, and unlikely it will, all of them will be equal to something here. So they are different, but we will destroy part of them being different. Okay.
But you don't really want to work non-equivariant.
No, even if we work equivariant, you can ask like, if I actually sit on the wall in my parameters, they somehow degenerate, how different they are. That's a valid question, but not what I'm going to discuss. So let me just state. So like that was the first way to destroy, to forget a lot of information, and I'm doing the second way to forget a lot of information. I localize. So both sides are modules over polynomials, Laurent polynomials in alpha and h bar. So on one side, it enters as K theory of a point. On the other side, it enters as thing associated to monodromies. And so given a module M, we write M block or M tensor over this thing. Fraction field. So informally speaking, we are considering generic parameters alpha and h bar. Generic monodromies on one side and generic fiber in K theory on the other side. One can make the statement more precise, like not invert all polynomials in alpha and h bar, but say which ones exactly you want to, and that will be some walls. But let's keep it the simplest possible.
So can you remind me how does the h bar alpha act on the A side?
Sorry, h bar. They are monodromies of e to the minus w. I just erased. Okay, like they enter as these guys.
Yes.
Okay, and they enter on the A side if I just choose a different branch. My cycle will be multiplied by alphas or by h bars. That's exactly the structure of the model. Okay. Straight Y, I explained. You take a cylinder with punctures and then take K points in. You don't have bundles here. So like curly Y will be bundled over it. But this is just a space. Just take K points on a cylinder with punctures. Okay. So the theorem is that after in my project with Smirnov, these things are isomorphic. There is an isomorphism. Of the downstairs things. And as written, it's very mild because I just take two vector spaces, and being isomorphic as vector spaces is not that much information. So in the rest of my talk, I'll just make more precise what this isomorphism respects and what it identifies. So at first it will be just, okay, dimensions match, and we will proceed. Not algebra. I don't want to think about that. I don't know how to phrase algebra here. And moreover, it came from triangulated categories. And there is no a priori fixed unit. I don't know what to compare. And you most likely, I want to allow derived autoequivalence that actually move it from somewhere away. So most likely this will not be an isomorphism of algebra. So that's, yeah. Maybe we can invent something that will match, but that's exactly the structure I don't want to consider. We will go there. Like once again, first vector spaces. These are vector spaces over this field. So we so it was just 1 hour, right? Okay. Okay. So first of all, isomorphisms as vector spaces. Which is the same as dimensions match. Sorry? Well, ground fields match. That, well, fields do match. Fields do match. That's great. Yeah. Yeah, after that, the next statement is dimensions. Okay, so dimensions, first dimension of one side is actually the number of the fixed points. So we already know that it's just choose number. Cool. Okay, and the other claim would be that dimensions of this homologies so there's 0 if star is not case. So it's if it's not middle dimensional case, and in middle dimensions we have exactly this. So middle dimensions see everything, and we have this. I'll go there in a second. But first of all, it's not. It's something people have seen from like late 80s or 90s. If we talk about not working on a cylinder but working on a plane, people who studied Knižnik-Homological equation considered this thing as being cycles of integrations to solve Knižnik-Homological equation, and they have seen that these are exactly the number of like similar combinatorics of cycles similar to the one that solves Knižnik-Homological. But now we're on a cylinder, so we solve trigonometric Knižnik-Homological by the similar thing. Okay. So, and if you want, like, this whole story started as y side has, even in the formulation of what y is, it has very close relation to Knižnik-Homological equations. And this should be like the space of conformal blocks. So, and conformal blocks are exactly like one of the ways how to construct them explicitly is just to take some sort of contour integrals. And these are actually the contours. I'm trying to compare contours in solving Knižnik-Homological equation to something that comes naturally from geometry on the other side. And there is something to expect there because quantum differential equation on B side is exactly trigonometric Knižnik-Homological.
All envelopes have choose.
If it's generic, so like local.
One of the question, only the question is because if it's all homological with one zero, then it's like the remaining.
So very abstractly, if you have CW complex, so homology are generated by cells, but what are actual maps depend on the choice of monodromies, right? And I'm taking them generic, so generically nothing changes. That's more or less the statement.
So you're saying generically.
That's what in localization means.
Localization.
Yeah, I said it here, so like,
Okay.
because I allow to invert some things in my torus, I see it at a generic point algebraically, and that's what I'm considering.
Okay. Can we frame this all like very explicitly? It's just like a P1 minus N minus plus 2 function, something like that. Looking at just.
Sorry, I don't understand your question. Just like I could state this statement if you give me a precise like what K and N you want to work with. I could say just look at this thing provided that alpha, let's say, is not h to some power. Like outside of this, where like you can list finitely many powers of h, outside of these planes, everything is good. Okay, so there's like something very explicit to say. Okay, are we good?
You mentioned something about matching the phase equation on the side with
Let's go there later. Just like differential equation. But on the other side, we also have differential equation. We can move the punctures, and that's Gauss-Manin connection. Okay. Yeah. Okay, so let's do k equals 1 case to convince ourselves that we can do it. So for some choice of not lambda 1, we can say we can look at the real part of W as a Morse function. And it will look, the picture for my punctured cylinder would look like, okay, here I have something that approaches to 0. Here I have something infinity and other punctures as well. Right. Let me just draw two. So Z1, and that's the picture. And for people who studied commuting the homological equations, they know that this thing has finitely many critical points and they're all simple. In this picture, I just have two. Right? And then, yes. Yeah, and yeah, I have exactly n of them. Okay, and what I'm trying to do now, what does Morse theory say me about it? It doesn't say that homology of all these things are related to critical points, right? It says something more subtle. It says that if I take whatever sits on in this thing preimage of these values before all critical values here, I know that the homotopy type, as I pass through critical points to here, it will be something. So if I write here, I will think about it as boundary y minus. What my Morse theory says me, Morse theory says me that homology of y with respect to this negative boundary of y with local system. All these points have middle index, just because it's holomorphic symplectic. So like as many directions down I have as many of them up. So this is 0 if this is not middle dimension, and number of critical points of W if this is middle dimension. Right? And it's not quite what we consider. We want Borel-Moore. We want our cycles allowed to go here. Okay, so how to compare to Borel-Moore? Or if I am to introduce the other boundary like y plus, then it will be the same as relative homology of y with respect to both infinities. So the number of critical points that it's exactly the same is known to people, but how do I compare between these two guys? And you see, I drew this picture for some chamber of these values. If I swap the chamber, some of the legs could pop upstairs. And if I'm not sure that all of them are just Borel-Moore, I will be unhappy about it. Is my statement clear? But I want to say that they are always generated by critical points. And as I vary lambdas, it's more or less natural that their number doesn't change. But due to non-compactness, actually it could change if one of critical points runs away, right? Okay, and what saves the situation here is that the homology of S1 with respect to rank 1 local system is 0 if lambda is non-trivial. Why? Because I have just two-term complex and the map, so I have C1, C0 generated by, let's even say, I have span of one-dimensional cell, span of zero-dimensional cell, and whatever I put here, it's actually 1 minus the monodromy. So if monodromy is trivial, if it's 1, I get both H1 and H0. But if it's not trivial, they cancel. Right? So corollary is that homology of the positive thing with respect to my local system. Recall, I considered generic is 0. Because I want Morse function. sorry, I think because you have log, right? Multivaluedness is because real value is controlled by logs of 1 minus the ratio, and it blows up to plus infinity or minus infinity exactly when you approach a puncture or far away, right? So that's exactly when something happens. Okay, so now if I write long exact sequence for a triple, I will have to, that connects one and the other. I will also have these terms there, and they are all 0. So I'll just have an isomorphism. So corollary prime is that, oh, which way I should write to make sure it's natural map? Okay, so if I'm taking this localized, then the natural map here is an isomorphism to Barrel-Moore, which is there, which is just imposing more relative conditions. Okay. Just because, yeah, just because this piece vanishes. So I started to look at this because at first I was not sure where I should allow my Lagrangians to approach and where I should not. And then it turned out that you should just allow to go everywhere as long as you consider generic local system. It just doesn't matter. And unfortunately, if I try to allow them to approach in one direction and then in another, for all objects I want to consider, there's this empty set of such lambda zeros and lambda ones where all of them are allowed to approach in a good way. So that was like an algebraic way to bypass and understand that where you actually allow them to end doesn't matter. Okay. And maybe one more similar thing, you can write that. I wrote everywhere Barrel-Moore, but I could write the natural map from just homology without any Barrel-Moore. Barrel-Moore. After I localize, is a nice mark. I could prohibit them to go anywhere to infinity, and it will still be the same. Okay. Okay. Since we discussed what the dimension is, maybe it's better to introduce what the basis is. Basis is if you choose a subset, a K subset of indices of the punctures. So I is just I1 at K. Then you could make the following cycle. Z1. Oh, let me write the numbers of this puncture. So it will be I1, IK. And I'll make the cycles that go like this. So it's exactly k-dimensional cycle. For each y, I just allow to go only along the corresponding circle. Right. So it's k cycle. And we will call this Fi.
So in the case, for example, k equals to 1, what are the compact cycles? Oh.
Yes. Maybe let me proceed and we will see how this actually thing works in more detail. How much time do I have? So when do we want to finish? Sorry? Before 4. Okay. Okay. So these cycles, they form a basis. And we see that just by combinatorics, they're exactly the right number of them. Of Baron-Moore homology with local systems. So each of them, because they are contractible, actually, each of them is just an interval. Because they're contractible, there is no obstruction to choose W on them. You have to prove it. That's indeed something you have to prove. I'm going there, yeah. But okay. To prove that there is some sort of correspondence, you have to first somehow independently show that they're bases. Yeah, I agree with Peng on this. Okay, that was just like as vector spaces, they're the same. Okay, what else do we get for free from knowing that they come from decategorifying some category thing? Yes?
Sorry, so in the k equals 1 case, the dimension is n, isn't it?
It is.
But you do k cycles or n cycles? How many cycles are there?
So they're exactly the choose number of cycles. Just for any choice of a subset, I get exactly 1 cycle.
Oh, okay, I see.
Yeah, so they're parameterized by the
So there are
subset.
choose k.
Yeah, exactly as as fixed points on the other side.
Okay.
Yeah. So dimensions match. Great. Okay. So what else do we have in category? So far, I just played with objects. In category, we also have morphisms. And morphisms give us pairings. So recall that the equivariant K theory just has a pairing that is, you just take R home or X if you prefer to call it that way, or between 2 sheaves, and just have an alternate in some of them. And in particular, this thing is well defined. Element in the localized K theory of a point. So it is actually a rational function on my torus. But it is like this by localization. I could write this as some sum over fixed points. And for each fixed point, I'll have some well-defined rational function. Sorry? R home is in the derived category, yes. Sorry? This could be infinite dimensional one. And I should play in 2 games, either consider them graded. Yeah, but that's K theory of a point. So if this is finite, this is just element in K theory of a point. Right? So it is actually graded vector space. So it's actually an element here, if I just take a K class of it. But this can be infinite dimensional, or they could be infinite dimensional archons. You could need actually infinite resolution. And then you play in two games. Either consider every graded component and see that somehow it stabilizes, or play an even simpler game. Just say that by localization theorem, you can compute it over fixed points. There are finitely many of them, and each of them is given by some sort of rational function, which is a better game because I actually know how these infinities could behave. They collapse into a rational function, which is a good statement. It's not just an arbitrary series over graded pieces, it's rational function. Right? When I compute this thing by localization, it will be there.
So suppose I use two sheaves F and G, and I compute the visual house.
Then it comes with gradients.
Then the T action, the house space has a T action.
Let's just take from O to some sheaf, right? It will be just sections of these equivariant sheaves. And we know that sections of an equivariant sheaf come with gradients. Or take like O to O, it's just like global functions on your thing. They come graded with respect to torus automatically.
How can the geometric sum collapse into a rational function?
By localization. By localization, you can compute.
Just like generating the parent. If something expansion there, the function is over. If something expansion there,
But we can have infinitely many of these guys. We're in singular case. We can have crosses. So they could be actually, because they're Cauchy resolutions more or less. And in this Cauchy, they are cut out by finitely many equations. Yeah, possibly, but okay. I think localization statement is still easier, but okay, whatever. Yeah.
You want a dimension.
Dimension of the arc.
The left-hand side is a number. Is there some magic that
No, but you well, what is K what is non-equivariant theory of a point? It's just number, the dimension. But what is equivariant key theory of a point? It's actually a Laurent polynomial, because it counts with weights dimensions of. Yeah, because I think K class of it. K class in KT of point. Yes. Yeah, K class of it. Okay. Okay, what should be the pairing for two middle dimensional for homology with middle dimensional thing? So it also has pairing. Okay. Okay, I'm trying to guess which one is better, but sometimes it doesn't. Okay, this one. Oh yeah, this one looks.
No, don't rewrite all. It's okay.
Okay. So it's just the intersection pairing. Right? I'll just now have two cycles. I have some intersections between them, and I'll say that taking one cycle and another cycle would be just the sum over the points. Well, if I deform them for everything to be transversal, then it's just points in the intersection with, in classical think, I'll just have plus or minus 1 depending on orientation. Right. But now I also have a section of my local system, S1 on C1 and S2 on C2. So it will give me some sort of gradient. It will be S1 at, let me write S2 at the point P over S1. And this is some monomial. I have a section, these two are sections of e to the minus w. So they differ exactly by monomial. So now I don't only assign a sign, I assign a monomial. Okay, and I can write this thing. So it looks good, but it's actually not, because the trouble is we work with Borel-Moore. So they're not compact. And that's very easy to change the number of intersection points. If, for example, they end here and there is no intersection, I could deform it to be like this and have some contribution. So not compact things are bad. Well, yeah, I'm going there to the solution. But we know that what is the right pairing for Borel-Moore? It pairs perfectly with the ordinary homology, because compactness is here already. And we know that after localization, in our case, we have that they are the same. So, okay. So I will think about, I'll take 2 cycles from here, map one by this isomorphism to this. Let me write it. So introducing a map. Map this isomorphism that goes from Borel-Moore localized, ordinary localized, and I'll call it C. The cycle C goes to CW. So then we say that C1 with C2 is actually take C1 with W. Think about it as this thing, and then write C2. And just now use intersections. And I'm pretending here that I don't know anything about Fukaya categories, but in a second we'll see that actually it is Fukaya category, some modified version of Fukaya category. Okay. To understand this, I actually need to play around my long exact sequence that gives this isomorphism and see how actually I should go from here to here. So let me think that I'm going to infinity circle that looks like this. And I have Borel-Moore cycle like this. So this is C1, oh, I call it C. And it's not cycle here, so I cannot just take it this. So what I'm doing to make it cycle in usual homology, I would add something on the boundary, right? That's exactly what comes in my long exact sequence of that gives me this isomorphism. So if I keep track carefully what I'm actually doing there. So here I have some section, let me call the value of section kappa here. So I will add one more circle here. And if it's kappa here, then here it should be, I should write the coefficients kappa over chi minus 1 and kappa chi over chi minus 1, where chi is the monodromy along the circle. So because I choose my local system section continuously, if I have it here, on the other side, I'll have here. And now if I compute this minus this, I'll get exactly that it cancels at this point. Right? And now I can just push this construction away from the boundary, and that will be my cycle. So I can just leave the boundary. And that will be my cycle that doesn't touch infinity at all. So when Peng's question was, how do you leave infinity? It's just by this, always. So if it was CW, I call this, sorry, if it was C, I call this CW. So we see that we now define the intersection at the cost of possibly introducing rational functions, as it was on the other side. Yeah.
This is only well defined after localization.
Yes. Yes, that's my point. Or some version, some modification that does similar job. But in a second. So let's do, assume chi is small. So we can just expand this rational function. So my CW then is, it's this thing plus circle. So let me, here I have kappa, here I have kappa. So kappa and kappa chi plus kappa chi to cancel this and plus kappa, I just mean I have a sum section here. So it has some value here. Is it clear? So like all ends here will cancel and they will become smaller and smaller. So another way to write it, it's exactly to write this and then merge it with this. Merge with the next one. And so on. So now I have this picture of that cylinder. And in Fukaya category, it's called wrapped Fukaya category. So when you try to compute morphism between Lagrangians, you have to modify one of them by wrapping to exactly make sure there is some sort of compactness. And we just see it. We see it algebraically. I don't even need to assume that I always expand it into power series, but it's exactly what we have here. So once again, I'm pretending that I know nothing about Fukaya category, it just pops out. The only thing you could do is, and you see, here it has beauty that here I had to care about something about convergence, and I really don't want to because I just substituted by this algebraic statement of localization considered generic behavior.
That's a naive question.
Yep.
So your superpotential is so your superpotential has like 3 plots. Like you have 1 minus y over yj.
Yes.
And 1 minus 3 zi over yj. But somehow you combine the first 2 parts, the interactions between the yi's and the interaction between the functions into a single term.
Yep.
Raised to the power of 0.
Yeah.
Is it possible to separate these 2 terms?
I don't see any reason. And unfortunately, it's how it comes if we consider interaction from this and upstairs thing. I just don't see any way to introduce more parameters where they behave naturally. Okay, so continuation of the theorem is that one could identify my Fi's with the structure sheaf of points under bijection. Again, bit choke. Okay, sorry. Such that it's an isometry. Okay. So these guys form actually orthogonal bases. And then what you have to check is actually what is their norm, and norms match. It's not quite strong enough to separate some of the fixed points here, let's say. So it's not quite the statement that it's the only thing that could happen, but we are going to the guy that will separate them. So now, okay, so far we did everything we could from just knowing that it was categories. And now the third part is a fine braid group action. So on A side, it's manifest. On A side, just move the punctures.
You have which one?
I will, but later. Just to show how it works, I need first to see this. Okay, so we can move punctures, and it's known that if you move n points on a cylinder, it's a fine braid group. So a fine braid group is the same as braids on the cylinder, braids, as opposed to planar ones when you copy the usual braid group. And here we have a big commutative subalgebra. That is just a puncture goes around. I move only one puncture and it goes around this without intertwining with other things. So I'll call this yi's. These are the elements they commute, obviously. So formally speaking, informally speaking first, when I move the punctures, all my cycles accordingly deform. Formally speaking, it's called Gauss-Manning connection. So that's monodromies of Gauss-Manning connection. And it's just manifested here. Okay, and what is on the B side? On B side, large commutative family is multiplication by line bundles. And you could identify line bundles and this thing. Let's try. And this guy, well, one can find L1, Ln that act on the fixed points in a way compatible with the action of y's on my f cycles on the other side. Just because when I move one thing, it's easy to show that it's just multiplied by some number. It just depends combinatorially on what I have from the left, what I have from the right. And you just see what are the restrictions of line bundles here, which are the values you need to multiply when you do this, and they just match. So, and this uniquely determines what are how fixed points correspond to the F branes. It's some another coherent sheaf. So it's just natural operation. So you see, going to the question about algebra, I don't want to consider algebra structure here, but I want to be able to multiply by line bundles, and that is the thing on both sides. But I don't know if I'm giving you some cycle, if it's what line bundle it is. Sometimes I can guess that it's a line bundle. It's a class of line bundle, but I don't know how to multiply. Which one is identity? Let's see. Which one? Just follow. Okay. But that's not all the story, because we also have Ti that exchanges I and I plus first place. We have this. And well, okay, on A side, again, it's manifest. On the other side, it's some sort of, it's Steinberg correspondence on B side. More or less generalizing Ginsburg construction that K theory of the Steinberg variety as a convolution algebra is a fine Hecke algebra. More or less what happens when you swap two points, that you look at this. A fine Hecke algebra. And these things even have approaches where they are categorified, like Bezrukovnikov in some cases does similar things by derived Steinberg scheme, like correspondence is coming from there. So it's also, so no, I use it only on K theory level, but it has some technically hard continuation into derived category as well. Which is great because here we see just it categorically. If I do Fukaya category, it will act. Okay. And this also match. One can compute it. Okay. Okay, so, sorry? We don't have multiplication between two things, but we have multiplication by line bundles. So we don't know the structure of algebra, but we have structure of module. So this guy acts on K theory of T star P1 by convolutions. And this is our K equals 1, N equals 2 case when we just swap two things on the cylinder. And Ginsburg actually constructed that on this scheme, you can consider some sheaf that push-pull of it will give you action of a fine Hecke algebra.
You can't translate the KT of this Ginsburg stuff, but the thing
yeah.
acts on, you can
yeah.
translate.
So
Interesting question.
it is, but it will be derived. So like, let's leave aside everything derived. So, okay. And now let me introduce. So far I considered only one basis, the F basis. Now there are new bases on A side. Okay, they will depend also on just a choice of K tuple. So they will be enumerated by the same thing. And they'll be just cycles that go this way. So I'll call this S plus corresponding to I. And similarly, I could do it going the other way. And it goes the other way to other infinity. And this will be S minus I. So now I reached the title of my talk. Theorem. Smirnov. Under the isomorphism that matches F things with OPs, S plus minus I are matched with the stable envelopes of the corresponding points. Again, plus or minus. So the guess was done by Mina, but now we have all the tools to actually prove it. So proof. So because we know that we have non-degenerate pairing and these guys are bases, it's enough to show that the pairing on one side with F enumerated by some other thing is the same as the pairing between stable envelope and the structure sheaf for the point. But what is this? This is just home. What's home from a class to a fixed point? That's exactly the restriction. Right? So we are going to show this, but it also is interesting on its own right. For these formulas, we have some combinatorial description in terms of intersection. In particular, we can see that in our A1 case, everything factorizes into linear factors with some explicit combinatorial description, which is hard to see. Let's say Smirnov has this version of stable envelopes in elliptic case, which is some big sum over trees. And there is no way to see how this formula factorizes into some linear factors. But this approach can give it. Sorry? Key theory? For that, we need to understand what kind of. So you see, what was my problem that I needed to localize? I didn't know to which endings I want to allow my cycles to end. The hypothesis so far is that if I carefully choose where I can end and where I cannot, maybe I'll guess that it's the right candidate for non-localized key theorem. But it is some sort of work. I don't know yet how to do it. But so far, we just have the restriction formulas, which is already so.
It kind of looks like we have, sort of, like the support of the cycle is kind of like the support of the sheet.
Yeah, exactly. So like if they go infinitely in one direction or infinitely. Yeah. Possibly, possibly, but I do it so far we do it differently. So the approach so far. So can I continue? So far, checking diagonal is easy. Checking the diagonal is easy. That they match. Like if I restrict stable envelope to the same point, we know what it has to be, and it's just the same. And after that, run recursion on both sides. By applying TIs. The one, did they just erase it? Yeah, I'm sorry. The one that swaps I and I plus 1. It is some sort of, I can do it pictorial on A side. I could do the Steinberg correspondence on the other side, and Steinberg correspondences behave well with stable envelopes. So what more or less I write that I have Ti S plus minus I is F. Sorry, I wrote it here. I Fj is the same as S plus minus I Ci minus 1 Fj. And then I can express this thing as one or two terms in terms of other stable envelopes. Actually, this one and another one. And I can write this as a multiple of the same thing or the same plus some extra thing. And this gives three-term relations that allow compute S plus minus I F J, knowing it for the smallest I, or if you want, or the smallest G. And well, if you take the smallest stable envelope, it's just the attractor. It has diagonal entry that we know how to compute, and all other are zeros. So just starting from this very easy case, you just show that because the same recursion works exactly in the same way on both sides, they just match. That's it. So we could describe what are the restriction formulas for stable envelopes on the K-theory side by just doing some combinatorics on A side. Yeah, that's it. Thank you for your attention. So far, we know it in full A1 type, but not further. So nothing will change if we consider, let's say, T star Pn. But when we have T star Grassmannian to 4, we start having some troubles identify what fixed points are. And it looks like to be exactly the same phenomena as Smirnov had with his trees when he tried to consider abelianization to compute stable envelopes. So we are trying to understand if the trees are the right gadget to say something about these things. We were just not there yet to present it.
But I don't think to tell the story, you need to solve everything you need.
Thanks. Yes.
In context of what my story, what I was thinking for part two. So can you think of some you mentioned the hyper algebra. So
Right. Well, but it's exactly the representation of a fine Hecke algebra that you have on when you just tensor multiply the fundamental. So it's just action of R matrices on the product of the defined representation of SL2. And just like you fix the weight subspace in it and see how the R matrices like in the most standard R matrices in this business act on them, and that's exactly the representation. Yeah. But you can have here even more R matrices. For example, when I act here, the formulas you get are exactly yeah, nobody asked me about it. In stable envelopes, you have one more parameter, alcove, something like some choice in Keller variables. And here there is such thing. When I said you go straight to 1 infinity, you could actually go not straight, but like with some sort of twisting. And that the number of such ways is exactly the affine braid group modulo some choices that don't matter. So it's more or less the alcove system in the Keller variables. So when you're doing this, you are actually switching to the next alcove. And you can compare the formula you get here to the wall crossing R matrices in K-theory in the paper of two Andreys, and they just match. So we just get wall crossing R matrices and Keller variables just for free. They're here. Yes.
Wait, so you said you were getting restriction formulas for the same workflows, right?
Right. Yeah.
So, but if I remember from the beginning of the talk, your same levels are all like
Yeah, like this very special Nakajima curve, right? Yeah.
I mean, already like the equalization formula, there will be some combinatorics on that side. Is it different?
Yeah, it will be sum over trees. As I said, like Smirnov can compute it, and like he computes it not in K-theory, like one level up in elliptic stable envelopes, right? But in particular, this combinatorics shows us that because all contributions come in pairs in some sense, that's always like a product of 1 minus some monomial, 1 minus some monomial, where they have very combinatorial explicit definition. And if you want, this gadget is aimed at another way to generalize it. So one is like take K-theory, go to elliptic thing, and that's done by abelianization. Another thing is just take K-theory and consider what is it in derived world. And if we have equivalence of categories, which is the project with Mina Peng, if we have this equivalence, we just take the cycles and they are derived version of stable envelope classes. Just some derived cycle. So if you want, like, we just check the foundation that from this, it matches in K-theory, so we can proceed.
Yeah.
Okay. But yeah, it's not that it's new formulas. We just checked them with Smirnov. They actually give exactly the same thing you could do. You could get from degeneration of elliptic stable envelope if you want. Yeah.
You mentioned it several times, the elliptic stable envelope.
Yes.
So I always have the confusion. How do I suppose I have some categorical equivalence? Before I just directly pass it down to K-theory, can I go some midway to elliptic stable envelope?
I don't think so.
Okay.
But maybe it's my lack of knowledge. For me, that's two different ways to generalize it, and so far, I personally don't know any relation.
So I think that the typical way from K-theory to upgrade one is elliptic stable envelope.
Yes, I would be very happy if one gives the other. but I don't know it. Do you know? Like, you know, and
I will boundary then okay.
But in this Fukaya story, you have to
between S and F? Between which cycles?
One kind of advantage to not thinking about is because this kind of categorical stable, they're not orthogonal, they're symmetrical. There's no one.
Yes, they are.
Oh, that's obvious.
That's obvious. Just from intersections here. Yeah.
You got to be able to bootstrap that.
No, that's obvious in the graph. Yeah.
Yeah. Well, seeing that there is zero intersection here in this picture or zero, like it's very easy. So semi-orthogonality is like some intersections don't exist. No, we could have harder things than they're canceled by differential, but most likely it will be just here. It's so simple that there is no like complication like this. These spaces are super easy to analyze. Like you don't have differentials.
Everything else, you have no homes one way, you have homes the other. How do you see it? Yeah, I think Berkeley modules.
But you have homes or derived homes? Homes or derived homes?
No, X of any kind. Like, you took your Vermont module. You certainly put the kind of smaller inside the bigger. But there's no map, no X from the bigger, no X of any kind from the bigger to the small. Because any Vermont module in the category can somehow sit below this to protect the phone. That's something you consider creating.
Yeah, maybe someone cut down the size of the homes because it's actually not true. They do go like because of the wrapping that you have, there's sort of if you decide not to wrap at all, you get that. So this would mean like, okay, I only want homes of a certain degree, not. But if you don't, then the state levels will not have categorized that between these guys.
But you, from some general grounds, know that they should be trying.
I mean, they have analysis statements for like grades and P2 and so forth, but that they use very special like stops and boundaries. You force it here to have. It depends on the details of just how. We know all such details here, and so we know exactly what's true. So we can just compare notes. There must be some, some.
Could be, but I'm talking about some arguments not based on this kind of thing. We have some threshold that we are already on the kind of K to the point condition, and some the ways it can be. Maybe but if you're in the categorical